Hi, my name is Luna, and today I'll be talking about three different types of collisions in AP Physics C and the equations you should know, and I'll explain the relevance of momentum and energy behind each of them.
Very briefly, since most of the discussion that's going to happen today is based off of momentum and energy, energy is a scalar quantity that is used to measure the amount of work that an object is capable of doing, and it's measured in joules. Momentum is a vector quantity that is calculated in kilogram meters per second, and it is a measure of how much motion an object has. For good measure, here is the non-physics definition of what a collision is as provided by Merriam-Webster.
The first type of collision I'll go over are elastic collisions, and the important thing to remember about elastic collisions is that due to the conservation of momentum, the total momentum of the system doesn't change, as well as the conservation of energy, which means that the total energy of the system won't change either. This basically means that in a perfect system, there are no non-conservative forces acting on either of the objects in the collision. And a non-conservative force will become more relevant as we enter the later stages of this video and explain a few different other collisions. But just for now, remember that in the elastic collision, both momentum and energy are conserved. Because collisions have everything to do with momentum and energy, when you're presented with a problem, you will either be trying to find the mass of the system or an object in the system or the velocity of the system before or after the collision takes place. So remembering that momentum equals mass times velocity, we'll end up with an equation that looks like this. And because we're talking about specifically elastic collisions, just remember that the initial energy of the system will equal the final energy of the system regardless of what happens to the velocities of the masses in the problem.
So for this problem, we just want to insert our momentum equation and then start plugging in values. And plugging in our values will eventually give us the final answer of 30 meters per second to the right. This problem will be solved exactly the same as the first one was, so we'll just go ahead and insert the momentum equation. But notice because the billiard balls are of the same mass, all we have to do in this problem really is insert the velocities for each ball and then solve for the final velocity of the first billiard ball, which will end up being negative 0.5 meters per second. Finally, here's an AP style question regarding elastic collisions. And we can see that in this problem, the correct answer would be A because only the vector values in A add up to the initial vector given by the problem.
To finally wrap up this section on elastic collisions, I'll show a few examples of what they look like inside of a perfect system. The second type of collision we'll be talking about are inelastic collisions. And the only thing that's different in inelastic collisions is that while momentum is conserved, energy is not. So when we're solving or thinking about any kind of inelastic collision taking place, we just have to consider the fact that energy is being removed from the system through negative work. In real life, non-ideal scenarios, we constantly observe non-conservative forces in collisions. This is usually through sound or heat, but a non-conservative force can be anything from friction to a drag force. So when solving for any value in an inelastic equation problem, we can take our equation from before when we were doing the elastic equations, but we just have to consider the fact that negative work is being done, so we'll just add in the work non-conservative into that equation, and that's how we'll go from there. Now I'll go over inelastic collisions and what they look like in real life as well as what they would look like in a perfect system.
As we had initially observed, a lot of energy was lost throughout the sound of that collision. In these slow motion shots, you can definitely see that it was not just the sound, it was a lot of the deformity of the objects, the cars themselves. I quite like these interior shots, which show that the conservation of momentum is definitely still applicable in these scenarios. Very important for this reason that the car absorbs most of the energy in the collision because the momentum is not going to change. And if the car does not absorb the energy of the system than the driver does. This is probably the best example of a inelastic collision in an ideal system. It does a pretty good job of explaining exactly what it is because we don't have sound, but we can very much observe that just like the car crashes, there is so much damage done to the body, there's so much deformity, which means that even though like we don't hear any sound, for example, this is still a inelastic collision.
The final kind of collision we're going to be covering are perfectly inelastic collisions, and what makes these collisions distinct from the other two is mostly that during the collision, the two colliding objects are going to be sticking to each other. Regardless, the momentum of the system is going to be conserved, although the way that we solve for the final velocity is going to be different. So our equation is going to add the two masses, and we are only going to be able to solve for a single final velocity. Just keep in mind that energy is not conserved here. And in perfectly inelastic collisions, it's like typically the greatest loss or transfer of energy out of the system. Being on the subject of perfectly inelastic collisions, a type of collision that isn't exactly a collision but is very similar to this same dimension of collisions that we've explored is a explosion. And an explosion is basically the same as everything we've just established, except for in reverse. So what would start out as two masses combined would then turn out to be two individual masses with their own velocities.
Immediately after the inelastic collision section, I did not stitch the practice problems because a lot of them did include this type of inelastic, perfectly inelastic collision. So here I'll try and make up for that and do a few more involving more energy and some involving this new equation regarding momentum. So for the first section of this problem, we get to use our new momentum equation with the two initial masses turning into one combined mass and plug in those values, we get 9.1 meters per second for our final velocity. The second section of the problem is definitely energy intensive, but it's not asking for the final energy left in the system. It's actually asking for the energy that is removed for the system, so the negative work. Following that logic, we know that work is equal to delta K. And so to find the negative work done on the system, we need to find the initial kinetic energy of the system and the final kinetic energy of the system and subtract the initial from the final for the work done. This next problem is very comparatively simple because we don't have to worry about energy in the system. We essentially just plug in our equation to find the final velocity and solve. Very similarly to the last question, and almost as simply, we have an explosion question, which is basically just the same thing, same ordeal. Plug in the equation, except for make sure that it's the one with the combined masses at the beginning for the initial velocity, and then find the velocity of the 65 kilogram person. Now that we have learned all three types of collisions, we can see the true robustness of AP-style collision questions. They're a lot more variable focused than any other example problems we have seen, but the concepts remain the same. We can approach A by just remembering that momentum is always going to be conserved and finding the variable forms for each momentum, that is, momentum initial and momentum final. And using those, we just set them equal to each other and solve for v, the velocity of the mass. I believe we've already done a problem not dissimilar to this one, so we'll just approach it the same way. So if we're trying to find the negative work done by the block on the bullet, we will just find the initial kinetic energy and the final kinetic energy in their variable forms and subtract them to find our delta K value. Moving along to C, we can go ahead and take our value from B, and the way we'll associate work with force is through the equation where it equals force times distance. We then want to plug in our delta K for force and then solve for D, which would then be our length. To finish off with section D, just consider that when the block is moving with the bullet, it continues to remove energy from the system.
Now finally we can take a break from solving problems and look at a few examples of perfectly inelastic collisions.
I like this example video almost more than I should because I think it does an incredible job of highlighting almost the degrees of inelasticity possible in every kind of collision. Obviously, the first two are losing kinetic energy, but the bottom video becomes a perfectly inelastic collision. This video does a great job of eventually showing us what an explosion is like. Of course, what I am referring to is the carousel system losing mass because of that guy.
I think I'll wrap up the contents of this video by just prefacing what exactly a glancing collision is. It's not a new type of collision, and it can in fact be any of the three kinds of collisions we've discussed prior to this. A glancing collision essentially just means that the objects are not hitting each other head on, or in a two-dimensional plane like we've seen in a lot of the examples. It'll just be a matter of solving for the direction of either object before or after the collision.
Here are just a few examples of AP-style questions regarding glancing collisions. They would be solved exactly the same as how it's been shown, and they just involve the angle. That's the only thing that's unique about them. In this problem, we know the momentum of the system is going to be conserved, but we might as well separate it into both x and y components. The y component of momentum is going to be equal to 0 because the masses and velocities of the objects are equal, but opposite in direction. Because the objects have the same momentum in the x direction, the total momentum of the system in the x direction will be equal to 2mv cosine 60. Because the momentum of the collision is conserved and then the masses will stay stuck together in the end, we'll set our 2mv cosine 60 equal to 2mv and then solve for v final. Here we'll just want to separate the vector quantities of both momentum and use them to solve for whichever diagram would fit this scenario the best. In this case, because both of the balls are of the same mass, they'll be moving perpendicular to each other. So all we need to do here is find the vector that has the angle that will add to 90 degrees and that aligns with what we know about the conservation of energy. So diagram D actually represents this the best. This problem involving vectors is actually a little bit interesting. So although the angle is there, this has more to do with the conservation of momentum and the change of direction that takes place in this system. The correct answer here will be E because the horizontal momentum is conserved, whereas the vertical momentum is changing, and so it's only changing in the vertical direction, which means that only E would make sense.